Okay, we will see the demo of analysis of rectangular slab section, how the slab can be analyzed with the help of MMS programs. So this program is completely based and made on the new code IS 456-2000. Okay, and this shows the graphical representation of the analysis of the slab section. So let us click design, program list. Okay, so this is the program. Graph for moment coefficient for the rectangular slabs which is supported on all sides. This is the program for a two-way slab. Okay. Okay, this page displays the different graphical representation of the moment of coefficients given in the code for two-way slab. Okay, we have two tables. One table is given by the code, that is for two-way slab with corner restraints, and in that case we have 9 conditions given in the code, right? And the other case is two-way slab with corners allowed to uplifted. Okay, so that is simply separated slab. In that case, this is the graphical representation. This red graph represents the moment of coefficients, that is alpha x positive, and this green graph represents the moment of coefficient given in the code, that is for alpha y positive. Okay, alpha x negative and alpha y negative are 0. Okay, and this over here we can see is the sorry, ratio Ly by Lx, where Ly is the longer span, Lx is the shorter span, and this varies from 1 to 2 because it is a two-way slab, and the increment given in this table is for 0.02. Okay, so for your required Ly by Lx ratio, you can directly get the values of alpha x positive and alpha y positive, and you need not do any interpolation, you will get directly the values. Okay, so this is how this coefficient graphically represented, right? Okay, now coming to the second case, that when the corners are not allowed to lift, the corners are restrained and you are providing torsional reinforcement at the edges, right? So let us see the graphical representation of the moments of coefficient, say for interior panel. Okay, so click this restraint slab. Okay, we can see 4 graphs. This blue graph represents the moment of coefficient for alpha x negative. A red graph represents the moment of coefficient, that is alpha x positive, and this black uh, graph represents the moment coefficient for alpha y negative, and the green graph represents the moment of coefficient for alpha y positive. Now we can see that the alpha x negative is found to be almost 33% greater than alpha x positive. Okay, so we can see the moment of coefficient alpha x negative is almost 33% greater than alpha x positive, right? And similarly over here also, right? So this is the representation of the moments of coefficient given in the code, and this is the graphical representation of its. Okay, now you can refresh and can see any other graph, for say we take the condition too short age discontinuous. Okay, just string slab, and you can see the graphical representation of this moment of coefficient. So once you get the coefficients, you can find the moments mx and my. This is the moment in the shorter direction, moment in the longer direction. Okay, so once you get moments mx and my, you can do the analysis of slab, which will make very easy for you to design the slab. Okay, so let's draw the graph. Okay, now this is the page where you have to give the sectional properties of the slab section. Say D is assumed to be 150, right? Now please use tab key to fill the data. So press tab key. Clear cover we assume to be 20. Okay, F5 is 415. Please enter tab key. F6 is 20, right? Now we can simply click this command calculate. Okay, now we can see four graphs over here. Okay, black, red, green and blue. This black graph represents when the slab is designed using 8 dia bar as main steel. When 10 dia bar is used as main steel, then you have to refer to red graph. When 12 dia bar is used as main steel, then you have to refer to the green graph. And when 16 dia bar is used as main steel, then you have to refer to the blue graph. Okay, now the question comes that why the graph for 20 and 25 is not drawn over here, because there is a condition given in the code that you cannot use the bar dia greater than d by 8. Okay, when you do d by 8, that is 150 by 8, then that comes out to be the maximum bar dia that you can use in the slab. Okay, so the diameter to be used in the slab should be less than d by 8, right? So in this case, when the thickness of the slab is 150, 20 dia bar and 25 dia bar are not applicable, right? Now this is a very beautiful program where you can directly get the spacing required for a particular moment. Okay, and say suppose our moment is 16 kilonewton meter, right? And we want to use 8 dia bar. Just click this button, okay, and scroll the pointer on the black graph, because when you are using 8 dia bar, okay, you have to refer to the black graph. Bring 16 over here and find the corresponding spacing. Okay, so I will scroll the pointer on the graph and bring 16 over here, right? So okay, let us assume, okay, 16, right? So we can see the spacing required is 134, right? When the moment is 16 kilonewton meter, right? And below you can see the minimum EST required is 180 square, right? And we are providing 375, so it's okay. The maximum allowable spacing is 300 and we are providing 134. We are getting the required is coming out to be 134, so that is safe. Okay, so this is how you can get the spacing when you want to use 8 dia bar as your main steel, right? Now suppose say you want to use 10 dia bar, then just click this option and refer to the red graph. Bring 16 over here. Okay, okay, so you can see that the spacing required is 206 and EST required per meter is 380, right? So which satisfy the condition. Maximum allowable spacing is 300, so spacing required comes out to be less than 300, so it's okay. The minimum required AST is 180 and we are providing 380 square, so that is okay. So this is how you can get different values of spacing for all the allowable steel diameters in the slab and choose the most economical. Once you select the select the diameter of the bar, then you can always go for the calculation of one-way shear slab. Okay, now say the shortest span is found to the shortest span of the slab is say 3.5 meters. Okay, right. Now press tab key. Okay, say the load on the slab is 18 kilonewton per meter square. Okay, then the steel which we get from this graph, say it was 315 mm square. Okay, then you just click calculate. Okay, so this gives the permissible shear stress and this gives the actual shear stress. As the actual shear stress is less than permissible, so it is safe in shear. Okay, so this is how you can find the spacing of the slab for the required design moment, and also can do the one-way shear check, right? So this shows the 3D view that how can you check for the one-way shear check, how can you do the check for one-way shear, right? So this is how, this is a very efficient program based on the new bylaws of the code IS 456 2000. So it's better to use this program for the design and analysis of slab section. Thank you.